All right, well, let's get started. Well, first of all, thank you for coming to a Friday session. I've been looking at the scores from all the various sessions, and it turns out that the repeat sessions always do better. I guess the speakers get a little bit of a practice, and they look at the comments, so they try to improve. So I'll try to do the same, but can't promise too much on improving already. My name is Tony Petrosian. I'm the GM for Amazon Aurora. I'll tell you a little bit about the organization just so you get an idea of how things work. At AWS, we have a team for Aurora, and the team has several parts to it. One part is an engineering leader that leads the Aurora Postgres. We have another engineering leader that leads the Aurora MySQL. We have a leader that leads the Aurora control plane, which is all of the workflows and coordination of keeping things up and running and going and upgrades and clusters and so on. And we have a leader that leads the release management, because you can imagine there's a complex set of versions out there and releases. So that's kind of the overall Aurora organization. We have a director of engineering. His name is Murley. He did the deep dive sessions for storage. I don't know if anybody went to that session, but he's the director of engineering for all of the Aurora, so he's the person who brings it all together. And I'm just the person who cracks the whip. Don't do a lot of engineering work. So let's get started. So this session, what we're going to do is just give a very quick intro, and then dive into a little bit of the Aurora architecture. And the reason for that is I want to tie the specific improvements and new things and how they relate to the Aurora architecture and why these improvements are interesting. So, and then we'll talk about the new stuff. So how many people use Aurora? All right, a good group. Aurora Postgres. All right, Aurora MySQL. All right. So how many people are new to RDS in general? All right. See, there's a reason to do a little bit of introduction. So for Aurora is our database for MySQL and Postgres. It's compatible with the Postgres and MySQL. But it's really intended to simplify running very large workloads with high throughput, where the availability, durability, and the security is somewhat built in and as part of the infrastructure for Aurora itself. So try to make it really easy to use MySQL and Postgres for high throughput, large workloads, and simplify, the pay-as-you-go model for it. And so this is just the general tagline for Aurora. Now, one of the interesting things to know about Aurora, well, how is it different from just Postgres and MySQL? So let me just say a few things about databases in general. When you look at a database engine, it has generally 4 layers. This is a gross simplification of a database. But at the top layer, you have the SQL engine, which is the thing that takes the connection, parses the SQL, and then does the optimization and decides how that query is going to be executed. You have a transaction layer, which is responsible for asset characteristics of a relational database. Right? So you have your atomicity and durability, consistency, and the isolation. Below that, there's a caching layer, which basically takes data pages from disk and caches it in memory, because databases tend to reuse data a lot, so the memory helps reduce I/O, and this is the model that's been around for decades. And at the bottom of it is what actually deals with the storage and logging of databases. Now, if you have a database, you have terabytes of data, you can imagine there's some processing related to actually getting the stuff on and off disks and managing that entire affair. So traditionally, people would run a database on a machine, or you might put a machine and some SAN or whatever to separate the storage. But in general, what you get is those 4 layers are stuffed in a single engine, single executable, that runs on some combination of disk and compute. And that's how databases work. What we did with Aurora, we took those 2 components and we split them. We took the compute and storage and pushed the storage in the distributed shared storage model for Aurora. And then the compute went to what you provision as an instance of MySQL or Postgres that you interact with. And we separated out the caching as well, because the caching is now tightly coupled with the storage. So this is the model that it runs. This distributed storage presents a volume, which is the database volume, which the instance running in compute sees as, oh, there's my storage stuff. The distributed storage gives you all kinds of interesting characteristics, which basically manages your change record management, the application of change records to data pages. It manages replication, detection of failures in disk or so on, and healing whatever parts of the storage that is broken. It maintains 6 copies of the data across 3 availability zones so that you have availability and durability, so the data is always available and the data is always durable and nothing is lost. And it manages the entire database as a distributed 10 gig chunks across hundreds or thousands of machines. And we picked the 10 gig because it's a nice number. It's small enough where we can do things fast. As you can imagine, moving a box is a lot easier than moving a grand piano. So these 10 gig chunks allows us to do faster replication, faster healing, faster recovery from failures. And the other things that you get with these 10 gig chunks is that you can add them forever. And this is how you get this infinitely scalable, infinite, 264 terabytes, 128 coming soon, and so on. We just add these 10 gig chunks as your database grows. So you don't have to allocate storage, and you don't have to do anything as the database grows. And these 10 gig chunks get distributed across lots of machines in order to give you the throughput that you need for your database. Now, and then we take all of the change records and all the backups and stuff them in S3, because S3 is a very good place to keep things forever at a reasonable cost. So when you do point-in-time recovery or you have backups with the 30-day retention, they're usually where they end up is in S3. Now, whenever you talk to Aurora people, they're always very excited about this stuff, and they talk about the architecture. And a lot of customers say, why do I care? So let's talk about why we actually went ahead and did this. Not just for the awards that we got for building Aurora, but because customers. And so we've had RDS for a long time. We just had the 10-year anniversary of RDS. We got some nice T-shirts for it. And throughout the years, we've seen customers demanding more and more from their databases, where you're getting into sectors such as financials and commerce, entertainment, media, gaming, healthcare, automotive, manufacturing, logistics, medicine, and pretty much every sector and every type of business that we encounter with. One of the interesting things they're doing is they're building really complicated applications to serve their users, and the user base is growing. And all of our customers, and regardless of the sectors, they're telling us, hey, we're building applications that run 24/7. And we need applications to scale because we have 500 million customers. Like, I don't know if you saw some of the demos in some of the other sessions, like Mario Kart. You know how many hundreds of millions of people play Mario Kart all the time? When is a good time to take the database down? Never. It's similar with education. Like, people go to school at night, self-study. All the universities have online courses. When is it a good time to, tell a professional, I'm sorry, the website is down because we're doing maintenance work on the database? Never. And across all of these sectors, the requirements for having a database up 24/7, uninterrupted and unhindered by administrative actions, exist across. So this model that we have, what does it do for us? So in the Aurora storage layer, we do the processing of storage, not just like, here, put some stuff on disk and then get it back from disk. The actual data processing for a relational database engine is pushed into this distributed model. And these are some of the examples of things that happens at the storage layer. So instant crash recovery. What does that mean? Well, what it means is that all the log records are continuously being applied to pages, right, in the distributed storage model. So when you're doing crash recovery, it's fast because you don't have to go and do the redo and crash recovery for 5-10 minutes in a traditional database. The fault tolerance, when we actually detect something has failed, some storage, one of those 10 gig segments has gone away, and being able to basically create a new one and bring it back. Creating database snapshots, backups, point-in-time recovery, clones, the scalability of read and write, being able to survive, have a cache that survives a restart of a database engine because we have separated the cache layer out. And the low latency replication, all the replication work. So this is all the stuff that happens in this distributed layer, which is not part of the instance that you're using to execute your transactions and SQL. And this is why when we do a clone of your database, or you do a clone of your database, or you make snapshots, or you do any of the administrative functions, you don't see an impact to your transactional workload. So gone are the days where you had to figure out how much capacity you need on your system so that you could have a backup window between 2 a.m. and 4 a.m. on Saturdays so you could get backups finished without impacting the production workload. Or who has ever heard of doing backups in the middle of the day during the busiest times? Well, nobody did that, but you can do that now. You can create clones that have zero impact on your production workload. So when you look at how people use databases, it's not just about writing an application. It's about, okay, we wrote an application, now we're going to run this application, we're going to operate this application for the next 5 years, and all the things you think through, oh, how do upgrades work, and how backups work, how would recovery work, what is my disaster recovery strategy? And so we built the Aurora distributed storage model so that we can push all of these stuff down to a layer where we can throw as much compute and as much storage as necessary to take care of those functions without impacting the instance that sits on top of it. So that kind of brings us to, the overall Aurora promise, which is you get performance and scalability, you get availability and durability, you get all of the security functions that you need to build your most critical applications and workloads. And it's fully managed for you. And so that is the promise, and this is why we went ahead and did what we did with Aurora. So hopefully that gives you some sense, and this is the end of my introduction to Aurora, so we can dive into some of the newer things. But I wanted you to have this picture in your head, because as I talk about some of the newer future, it relates to the architecture. So let's go take a look at that. So what's new? I'm going to talk about some stuff that we did over the last year. So some of you might have heard of them. Maybe you went to sessions over the last few days. How many people have been to Aurora sessions already? Okay, so a handful of people. So I apologize for some of the repeat stuff. This being the Friday and the last session, you can't really avoid some overlap. So let's dive into the global database. So what's the purpose of global database? Well, Aurora runs in a data center in a region, in an AWS region, and within the region there are 3 availability zones, and all the storage is distributed across those availability zones and so on. But we have customers who are saying, listen, I need 800 miles distance between my database replicas because I have regulatory requirements, or we have corporate governance rules that says so, or I just want it, or it's part of my risk mitigation. And we have customers with different risk tolerance. So we built global database so you can replicate an Aurora database across regions. So this came out some time ago in 2019, and you were able to make 1 replica. And now what we've done is that you can create 5. So this is the new part of the global database. You can create up to 5 regions that hosts your database, and we replicate it. And you can also create a global database from an existing database, whereas before you had to create a global database from scratch. So if you already had an existing database, you couldn't add replicas to it, but now you can. And before the end of the year, hopefully, within a few days, we will have this available for Aurora Postgres as well as Aurora MySQL. So what does the picture look like? With respect to the architecture that we talked about, the replication task of moving the data from wherever your primary is, where you're doing your reads and writes, in this case, in this picture, it's Ohio. You have a primary in the red color, and you have a couple of read replicas. And whatever changes that are being made is being pushed down to the storage layer, because, of course, the storage layer manages everything. And then the replication task between regions is again managed by the storage layer. So one of the benefits is that you don't see the computation, the memory, and space requirements of holding the backlog of things that need to be replicated or burning the networking or whatever resources necessary for the replication, because, again, it's pushed down. And so the replication has very little impact on what you do other than, hey, you have copies of your database in other places. In other regions, those replicas are read-only, so all changes get propagated. But you can take one of these read-only regions and turn them into your primary region, so you can do a read-write, so you can do fast failovers. And less than a minute to do a failover between, say, Ohio and Oregon, or between Ohio and West Virginia, Northern Virginia. As you add replicas, going from 1 to 2 or 3 or 4, you see no impact to your workload because, again, those tasks are pushed down. The other interesting thing is if you do replication, either physical or logical, it's probably because you're trying to build a system for disaster recovery or some type of a durability thing. So you're assuming there might be a failure at some point. Otherwise, why would you have it in the first place? OK. So assuming that there might be a failure at some point, what actually happens when something fails? So what if a region is down or the network is down for 5 hours? What happens to all the changes? Well, in a traditional situation, you're holding all those changes in your primary instance and then hoping the network comes back and you do the catch-up and all of that. In case of Aurora, all of that just lives in the storage layer, and you could have a day of disconnected without impacting the operations on your primary production region, because changes get stored, and the changes that we stored for replication are the same changes that are used for backups, point-in-time recovery, right? And like for point-in-time recovery, you can have a 35-day retention. So we already store all the changes anyway. So this is how this infrastructure that we've built easily maps into this new features that we're building. It's just like, OK, another use for all the changes that we record in storage, and now we can do global databases. The other scenario that customers use other than disaster recovery with global databases is that these replicas that exist in other regions are readable. So you can run queries against them. You can use them for any kind of a read activity. So you can localize your reads. So you could choose to say, I have a product catalog, and it's really big. And the product catalog is maintained in Ohio. And then we replicate it everywhere else. So in other regions, you can access the product catalog really fast. Now, the maintenance of the product catalog is centralized in one place where you do the writes, but the reads are distributed everywhere, so you can have fast local reads. So that's another scenario for global databases. All right, moving on to another new thing. So cloning has been around for some time, but we've added cross-account cloning recently. And the reason cross-account cloning is important is because a lot of customers are telling us, hey, listen, we don't clone a database for developers and testers to play with in the same production account, because that would be insane. So please allow us to do clones across accounts. So with this, you can now take a database and clone it every morning and into a different account, which is used for your analytics workloads. So people can go do large queries or whatever it is that they want. Or you can clone the database for production, for dev and test work. You can actually take a database every morning, clone it, and these clones have no impact on your production workload, right? Because we don't even copy the data, and they don't even cost unless the clone starts to change. Because cloning is kind of like a fork. You fork the two copies, but you don't do anything unless something is changed. So all the clones point to the same piece of data unless the data changes, and that's when they diverge from each other. So in the case of analytics, if you're not changing things, you're just creating a clone which gets mounted in a different instance, and you can hammer it all day long. You can also make clones in a different instance and drop some of the data that you don't want to be seen as part of your analytics, and then have that clone be available for query processing. So being able to do these cross-account is, the thing that makes it really useful for these scenarios where you're using the clone for a different purpose than the initial production workload. Now, people have been using clones for testing, upgrades, and things like that for a long time, but now we think that this helps people actually use clones in other production scenarios. Okay. Another interesting thing which we've been working on, and it's been out there for some time, but we've also now added Postgres to our Aurora Serverless. And Aurora Serverless is really cool because you can have an instance of Aurora and you have a database and you use it for, 4 hours. And then you stop using it and the instance kind of goes to sleep and goes away. But because the storage is managed completely separately, that storage layer is still active. So let's say you have a clone, you have a serverless instance and you used it and you made a bunch of changes and then you stop using it and the instance goes away. And then backups still happen. If something goes wrong with the storage, still gets fixed because the storage layer is taking care of it. And you don't have to bring back the instance to do any of the maintenance work related to storage, right? So the next day when the instance wakes up because you're trying to do stuff, it's not like, oh, wait a minute, I have to go and catch up with the backups and this, that, and the other, right? Because that's all being handled. So the way the serverless stuff works is that we have a pool of instances of various sizes that are kind of sitting in a hot pool. And as soon as an instance gets a connection in our request router, we bring in one of these spinning instances, we attach it to the volume from the storage, and off you go. So it's a nice scenario because there are lots of databases that aren't being used 24/7 because maybe you do some data processing for some business-related activity 5 times a week or once a week or 3 hours a day. And so this is really a cost-effective way of doing data processing where you're not paying for these instances that are just sitting around most of the day doing nothing because you have some 4 hours of processing work to do. It's also really useful for development and testing because the number of time that I've personally spun up an instance then forgot about it because I did some tests and then I went to lunch and then I came back and then I forgot to drop it. And then at the end of the month, I get my bill and go, right? So if you're just using serverless, it's just automatically those things just go away, right? And so you don't end up paying, right? So if you're working, 8 hours a day, you pay 8 hours a day and then it goes away. We also have a lot of workloads which are very unpredictable in nature. Sometimes they're big, sometimes they're small. So using the serverless and auto-scaling capability of serverless really helps. Like I said, it's now available for Postgres as well as MySQL. So if you haven't tried it, give it a try, see how it works. It has had an incredible adoption, by the way. The number of instances in Aurora that are serverless is a little more than we expected, but it's really cool. All right. Let's talk about something which is really new. So we just announced this on Tuesday. It's an integration of machine learning with databases. If you think about AI and ML, the entire thing revolves around data, right? I mean, machine learning and AI, everything that enables it is about the data. So integration of AIML and databases is just a natural thing. So today, you build a model that predicts something, and you train the model using some data. And then you write an application that, I don't know, connects to the database and pulls out a record for a credit application for Tony. And then you run this through some model, and it says, Tony is not credit worthy, right? And predicts that I may not pay back, and so you decide to reject, right? But the execution of that model happens outside, which is good. So as an application developer, you kind of have to go to the database, get the data, figure out how to format it appropriately for the call to the AIML model, then make the call, get the results, and format it again as part of the output. So there's a lot of machinery involved that makes it a little less convenient. So running a ML model on a row of data in a database isn't as simple as saying select min, max, average in a database, right? Where it's just a function you call. So we thought, well, what if it was that simple? So we decided that, well, we have SageMaker and we have Comprehend, and if we could integrate Aurora with SageMaker and Comprehend in a way that allows you to access ML functions from SQL language, then a lot of database developers would be, quite excited about it. And these are some of the problems that we were trying to solve, right? Allow use of AIML in the database within the language of the database developer and not the data scientist. Because you have a conversation with data scientists and they start talking about their Jupyter notebooks and whatever, and you kind of lose track of what they're saying. So how do we do it in the database language, which happens to be SQL? And how do we do it so that it's high performance? So this is what it looks like. So we now have a function in Aurora, which is AWS comprehend.detect sentiment. And that function is kind of like min, max, or average, or any other UDF you might decide to have. And so you can do select star from user feedback, where you call AWS sentiment analysis with the column name feedback, which has a text. And then you say it's English, and you're looking for positive comments. So imagine that we collect all your feedback, and we store it in a database, and I go to see how many of you made positive comments about the session, and how many of you made negative comments about this session, and I'm sure you'll all make very positive comments because this is a great session, right? All right. So the way it works in Aurora, you have an application runs that select statement. The Aurora engine then takes that, runs the query necessary to generate the data, which is the user feedback column from that table, and then takes batches of rows from that and formats them in an appropriate format for Amazon Comprehend sentiment analysis. And then it gets the results back, and then it does it until all the rows have been satisfied. And then you get the response back in your application, the same way as you would get the result for sum, or a min, or a max. You would get a column in the results that says positive, right? Or you do a count, or whatever. So this is the idea. Now, something like Comprehend, which is the sentiment analysis, is already built in. So it's not a function that you have to do anything with. But we also have the APIs for SageMaker. So you can actually go build your own models, any model you want, train it, run it in SageMaker, and create a UDF in Aurora that basically points to that. And again, we'll do all the work of formatting, making the call, doing the batch APIs, getting the results back, and displaying it. Now, one of the cool things about this is that the separation of the compute for ML workload versus the database workload. Because you might have a model I don't know, for credit analysis or, I don't know, something else, which is really complex. And you might be running it on 100-node clusters with GPUs, right? But you don't want to put that kind of compute in your database just so you can do ML. So you might have a small database that makes a call to a giant ML cluster to get a model execution, and then you get the results back. So you can scale these things separately. You can scale your compute separately for the database. You can scale the storage separately for your database. And now you can scale your ML infrastructure separately for your execution. This is available in MySQL Aurora, and it'll be available for Postgres Aurora sometime before end of this year. So the next latest version of Aurora Postgres that comes out will have this payload. So I'll take one question because you were really...
How's the pricing?
Yeah, so the pricing, the way it works is there's no additional fees from Aurora because we're not doing anything, right? We're just making a call. So whatever the pricing is for Comprehend and Amazon SageMaker, that's what you pay for. So if you choose to have a giant SageMaker cluster or a small SageMaker cluster, we don't look at that. So it's priced separately, and each service does its own thing. All right. We think this ML integration is really interesting because the way it's integrated, that simplifies it for SQL developers. Another thing that we've announced is the Amazon RDS Proxy. It's in preview. We will have the Postgres version coming out shortly for preview, probably early next year. And the idea of proxy is you have applications, you may have application servers that create lots and lots and lots of connections to the database because maybe you have lots of users. But these connections aren't all active at the same time. So you might have 1,000 users connected to some application that's connected to the database, and I don't know, the user's having a coffee, and you're still paying for that connection that's sitting in your database. So being able to multiplex those connections, so you have fewer connections that are active to the database, right? And the database isn't being impacted by opening and closing lots and lots of connections, is a good way of thinking about the proxy. So it does the connection pooling. And it does the auto-scaling necessary with the number of connections to the database to actually satisfy the actual work as opposed to just number of connections. It also gives you the ability to have connections open and keep them open from the application. So from the application perspective, you don't have to go through connection and authentication all the time, right? So you can keep those open because they're now open to the proxy and they're not really impacting the database. So now you can have, I don't know, 50,000 open connection to a MySQL database, and the MySQL database might only see 1,000 connections that are actively doing stuff. Other benefits of the proxy is that we now have built some security mechanisms in the proxy. So the credentials necessary to connect to the database is managed at the proxy. So you can basically use secret store to store the credentials for the database, and the proxy uses the secret store for the credentials. And then you create IAM roles for the application to connect to the proxy. So you no longer have to share database credentials with the application. You don't have to put, I don't know, passwords in the app config files and stuff to connect to the database. So that separation makes it a lot easier to manage security and build more secure applications, right? Because now you have centralized management of credentials to the database, independent of management of credentials, and granting an application access to the proxy. And you can also manage those. So you can say, I grant access to the proxy to this application. So the application gets a token from IAM, connects to the proxy, everybody's happy, and the application has no concept of what the credentials were for the database. Now, one of the reasons we go ahead and build stuff like this is because we see a tremendous increase in the number of serverless applications that people are building. And so I don't know, a few years ago, if you were building an application and you had app servers and you were tightly controlling how many app servers, how many connections from each app servers, and connection pooling from the app server to the database and all of that. All of that kind of goes away if you throw a bunch of apps in Lambda and something, happens and triggers, and all of a sudden you have 4,000 Lambda jobs running, all wanting to connect to the database. So you get this burst of activity that comes from Lambda and hammers the database. Well, in this case, the proxy takes the brunt of that, right? Connections coming in, connections going away, that dynamic nature of lots of connection, open, close, open, close, open, close, simultaneously. The proxy is fully managed. You don't have to spin up instances. You don't have to choose instance types and sizes. We basically look at the traffic and what's coming to us from your application. And we also look at the database that you have. So if you have a tiny database, we just assume, okay, well, you're probably not going to try to get a billion connections to the tiny database, right? So the proxy is sized appropriately for the type of database that you have. And then it auto-scales and it manages the affairs so that you don't have to think about managing the proxy. You enable it and off you go. So it was launched, I believe, on Tuesday. So you can go and give it a shot. Like I said, the Postgres version will come. And this is the beginning of a journey. So it's in preview. We're going to put a bunch of additional features. It's important to share your feedback with us because we go build this stuff for you, not for us. So knowing what it is that you need and what works and what doesn't work is always, always appreciated. How many people use Performance Insight? Not enough people. So Performance Insight is our mechanism to give you information about your databases. The mechanism is there now. We have recommendation that also ties to Performance Insight. And this is how we will continue to add more and more information that you need to build your application, manage your application, right, and know what's going on with your databases. So we're investing heavily in Performance Insight, and this is our path forward. So every time you think, I wish I knew what was going on with this database, when we actually go and try to enable whatever metric that you want to see, it's going to be through Performance Insight. We've made some new improvements. Now you can get SQL statistics for queries and see what is going on. There's a bunch of improvements that we've done in Postgres, and now we're going to also add those for MySQL. Sometimes, you do a little bit of a staggered work. Shows up in MySQL, then shows up in Postgres, shows up in Postgres, then shows up in MySQL. Sometimes it's really not possible to do it all instantaneously. So instead of just waiting, we do it opportunistically. So we enable the Postgres stuff, and then we'll enable MySQL stuff. But I want to make sure that everybody sees and knows about Performance Insight, and that I wanted to share with you that this is our path going forward for sharing actionable insight about your stuff, and it'll be through Performance Insight. Those of you who use it, if you like it or don't like it, share your feedback. It's easier to iterate on this stuff. We have database activity streams. This is really an important piece for lots of organizations that need to know who touched the database, what they did with it, and when they did it. So it's your audit log. Now, traditionally, you go to your database and turn on audit log, right? And you have a high throughput transactional database. The audit log just fills up instantly, because it generates an audit record for everything that's being done. It's usually massive amounts of data, and it ends up in a file, and then you have to go figure out how to process it. So enabling audit logs has been a complicated thing. So we wanted to make it a lot easier. So the way it works is we basically take all the activity that's going on with the database, Bob did a select on Tuesday, and Mary did a insert on Wednesday. And we send it as a stream into Kinesis. And Kinesis being the stream processing, right? And it's persisted, and you can have it for a long time. Then you can do all kinds of interesting things. For example, you can say, I want all the audit records, but I'm not interested in looking at it unless somebody forces me to. So I'm just going to point Kinesis to S3 and just dump it there. And that's it. That's the extent of what I'm going to do. Or maybe you'll decide to, I don't know, run an Athena query on all the stuff that you dumped into S3. Or maybe you'll have a Redshift cluster spun up and create an external table, points to S3, and you do some analysis of your logs. Or maybe you take that Kinesis stream and you basically point it to third-party database activity monitoring systems, like and to get consistent reporting of database activity with your Aurora databases as well as on-prem databases that you might have that uses the same system. But the idea here was, how do we simplify it so you don't have to manage the audit stuff, and so that audit doesn't impact the database so much, right? Now, obviously, the generation of the audit record does take some amount of resources from the database itself. But we try to get those audit records off the node as fast as possible. So it's just about the generation, not the storage and processing and propagation. Works for Postgres. We'll have it working for MySQL early in next year. So like I said, I go out and beat people up to get the stuff done. So hopefully it'll be soon. So that's database activity stream. Other new things. So we've had this read replica. Everybody's familiar with Aurora read replicas. You can have up to 15 read replicas, and you can run your read workloads against read replicas. Nothing new here. But one of the interesting things is that the number of customers that just have 2 instances, a read-write and a read, is like huge. A lot of people just run 1 read replica and 1 read-write replica. So we said, hey, why don't we take this opportunity, and for this large number of customers who just have 2 instances, and just turn them both to read-write, read-write. And so that's what we did. So if you're just running 2 instances, you can actually try out what happens if both of them are read-write. And now you don't have to make the distinction of the read versus write, and so on. And you could use it the exact way you do now, like send the read workload to the right one and the read-write workload to the left one. But the benefit is with this that you get continuous availability for writes. Because if one of them goes away, you can just continue writing. So it makes it, your failovers even faster. So today, when you have a read-write replica and a read replica, and you do a failover, and the read replica has to do some work to become a read-write replica. In this model, the replica just is read-write, and it just moves on. You can also do some interesting read scaling by, let's say you have, 10 tables, and you write to the, and you have these 10 tables are broken up between your own tenant A and tenant B. And you can do all the writes for tenant A tables in the left one, and all the writes for the tenant B on the right one. And these are non-conflicting writes that can go just in the normal speed, because now you're not coordinating any kind of a conflict between these writes, because they're writing to different tables. And if there is a conflict, if you just happen to be writing to the same exact row from 2 different instances, the storage layer in Aurora will serve the one that succeeds and rejects the next one, so you basically get one of those errors that says, hey, this couldn't be serialized, right? Because it's an optimistic concurrency, so there's a winner and there's a loser, and then you retry. So that's basically how the multi-master works. Again, this is something we just started doing not too long ago, and the plan is to just invest in this path going forward and add more and more replicas. And the way we'll do it is just we'll just add the capability as we go on, right? So if you have tried it and you have feedback, let us know. If you haven't tried it, you could give it a try. But basically, the scenarios are, if you have a read-write and a read replica, and you could switch them to read-write, read-write, and continue on the way you work, or you could do split read-writes for different workloads in the same cluster, and you get better write availability. Now, if you have 8 replicas and 1 read-write replicas, and you want to do 8 masters, you'll have to wait a while until we make sure that it all works and performs and so on. Okay, what else have we done recently? Another interesting thing we've done is the federated query for Athena. So one of the things that we see is a lot of our customers are building applications where maybe in the past, the application had different data types and you put them all in the same database for sake of convenience. But now those applications are moving to the cloud and the developers are looking at it and saying, I'm doing a select of a blob object from a database in my app. And that's kind of not a best use of money, because if that object was in S3, I would get better price performance for large objects. And you're writing the code, and you're thinking, I could just do a get object just as easily as I do a select from a table. So pretty soon what you see is large objects, binary objects that used to be stored in the database start migrating to S3, because that's where you get the best price performance for large object storage management. You also get really good set of APIs for managing large object put and gets. Probably better than any relational database could ever do for you. So stuff starts to move out of the relational database to systems that are able to give you better price performance. Now, it may be that some stuff moves to databases like DocumentDB because, I don't know, you have a giant doc and you want to index it differently. And so what ends up in the relational databases is really the business logic and core transactional workload that really needs the relational capabilities. So as data gets diversified across different engines in the back to give you the best price performance, you end up having data in multiple places. So now if you want to query something that happens to be in 3 places, well, how do you do it? And this is where this federation comes in, where we're trying to integrate through the systems that are capable of hitting multiple backends. So in this case, with Athena Federated Query, you can literally run a query that touches DynamoDB, as well as Redshift, as well as Aurora. And you could do this with MySQL or Postgres, and do joins and whatever in Athena, and get the results that you want without actually moving the data. So we are having to do the continuous ETL or whatever that some do to make sure that the data happens to be everywhere and there are copies of it everywhere. So there are lots of scenarios that you can enable once you have federation. So I'm going to talk about another one of these, which is Amazon Redshift Federated Query with Aurora. And so this one just launched, and again, right now it works with Aurora Postgres as well as RDS Postgres, and the MySQL one is coming. And so lots of people use Redshift for data warehousing or do analytics. So you have data in relational databases, and you copy it out, you ETL it, and you put it in Redshift. And lots of people do this because you don't want the historical data to be in your relational database causing bloat for your production application, so data moves. You also might choose to take really old data and put it in S3, because again, like I have data that's 10 years old. I really don't want to throw it away because somebody might need to query it, but I also don't want to pay for it to be in active databases. So maybe the 10-year-old data moves to S3. Maybe the last 3 years is in Redshift, or maybe the last 8 years or 7 years, depending on whatever the requirements are for that business, ends up in Redshift. And then the active data is in, let's say, Aurora Postgres, like the up to the minute. Now what if you want to run a query that does give me the revenue for last year, last month, last 10 years, last 10 years by quarters. And then at some point you say, I want the revenue up to the last second. Now it requires that you go after the active system. So with this, you can actually create these external tables in Redshift that reference a table in Aurora. So a table in Aurora is now accessible by Redshift, and you can create views in Redshift that does a union of all the tables in S3, in Redshift, and Aurora Postgres. So maybe most of your analytic workload just hits the tables in Redshift, but every once in a while, somebody wants to run an audit thing from 10 years ago, and you can basically run the same query, except you run it against a view that includes S3. And maybe every once in a while, somebody wants to see the up-to-the-second data, and then you hit the view that includes the Postgres table, or you just reference the Postgres table directly from Redshift. And in this case, whatever the infrastructure that you have in your analytical system is available for joins and other aggregations and so on with the active data that happens to be living in Aurora Postgres. So these federations, active federation mechanism is really useful when your data ends up in different places and you don't want to always copy an ETL data back and forth all the time, right? So you could just leave the data where it is and do the work. The other interesting thing about this stuff is you might have data that has different compliance and security requirements for the active production data that lives in, say, Aurora. And that might be different from the way you manage the compliance or security of the historical data. Well, in this case, because the data security and compliance managed by Aurora and whatever policies that you apply there remains, even though you're trying to query it from Redshift, it's still being governed by the source compliance and security rules that exist for Aurora. By the way, the same thing is true for all of those AIML integrations. Because the data actually never leaves, only people who have access to run the query in Aurora get to call an ML function, and the security of the data is managed in the same place, just as we have here. So this is the difference about federation versus copying stuff around, because when you copy stuff around, then you also have to manage all of the compliance and security rules and regulations and the governance along with it. Whereas in the case of federation and integration with ML, the source is where everything is governed. So let me just show you a couple of things. This will require glasses. So this is the query editor. Oops. This is the query editor if you go to Redshift and you say you want to run a query. I'm just going to run this to show you. So there's a bunch of tables, and so you want to run an ad hoc query. And so I'm going to let this go for a second, then I'm going to pause it so we can talk about what is actually going on here. Okay. So I'm going to select count star, comma, min ship date, max ship date from apg.lineItem. And apg.lineItem being Aurora Postgres.lineItem. So this references a table which is actively managed in Aurora Postgres. And I'm just going to do a select on that table. But I'm in the Redshift query console, and the actual query is happening in Redshift. And so you get an answer. There's like 30-some thousand rows in there, and the date, min date is 2019 January, max date is March. So there's like 3 months of data in there. Great, so that's your active data. We just queried it from a Redshift query editor. And then we're going to go ahead and basically run this query again, but instead of Aurora Postgres, we're just going to do it from the schema that exists in Redshift. And in this case, you have a few million rows, and the dates are ranging from 2015 to 18. And then we're going to do the same thing, except we're going to reference that table from S3 and run the same query on S3. And you'll notice that this one is going to take a little longer because we're not hitting a fully managed index table in Aurora or Redshift. It's just a bunch of data sitting in S3, and results will come back. And it's 6 billion rows, and the date ranges are from 92 to 98. So there's about 6 years worth of data in there. So you can see that we're just sitting in Redshift Query Editor querying tables that happen to be in 3 different places. So now we have a view that we've created. So we're going to look at this view definition and see what this view looks like. So the name of the view is line item all, and you can imagine what that is. So line item all happens to be a view which does a union all of the table from Aurora, a table from Redshift, and a table in S3. And then, then you can run queries against this table. And now you're querying table with historical data sitting in S3, with active data sitting in Redshift, and up to the second data sitting in Aurora Postgres. And you never move the data. And all of the security and compliance machinery applied to S3 and Redshift and Aurora are appropriately for those sources and managed by those sources. So here, we're going to run a query against the view and look at the plan. So you can see the actual query execution plan on Redshift and how Redshift is reaching out to these different sources and pushing queries down, pushing filters down to those sources, bringing only the data necessary to satisfy that query. So the significance of this one is this is looking at orders that had a quantity of 10. So as you can imagine, you don't want to bring all the data from Aurora to Redshift just to filter out and throw it away. So the query filter is being pushed down. So Aurora will only return rows with quantity of 10. So we'll right? And then the query then gets aggregated at Redshift. And again, this is an interesting thing because you might have a very large Redshift cluster because you have very large volume of data, or you might have a small cluster or whatever. The compute is appropriately sized and it's independent of the sources. So again, you can cost optimize the best way for the workload. So that's kind of the Redshift federation. And the reason I wanted to cover this at length is because I wanted you to understand that the direction we're taking with Aurora. We're not trying to make Aurora everything to everyone for every workload, but we're saying within AWS, we have analytic systems, we have machine learning systems. So instead of taking all those things and stuffing into one database, we're integrating the database with all of these services so that you can get the best of each service, but without having to do the work necessary to integrate yourself, right? So you can run an ML model on a giant SageMaker cluster from Aurora without actually doing any of the integration work. You can run a Redshift cluster to do analytics that touches Aurora without having to do the work. And so this is an investment area that we will continue directionally to integrate the databases with all of the other services, because the applications that you're building in the microservices that you're building for your applications do require different types of services and a variety of services that you're using. So we want it to be as easy as possible for the data to be used across the application and all the microservices that you're building. So hopefully that gives you a little more idea of where we're going, and it's not just about the feature that we happen to be talking about here. I know that this is probably the last session, so maybe not so relevant, but the recording of all of these is out there. So if you really want to get into the weeds with how Aurora storage works, including how we apply change records to pages and how often and so on, that first session, DAT202-R1, demystifying the Aurora storage. And then we had a deep dive session for Aurora MySQL and a deep dive session for Aurora Postgres, which just covers each of those subjects. And then a bunch of sessions on migrations, and then there's a session which is all about RDS that you may want to check out. We have some new training site, so this probably showed up in all of the sessions, but Visit aws.training to see what's out there. We're going to start putting a lot of training material there because we're building a lot of new services. And then I'll stop here. Thanks a lot. My name is Tony Petrosian again. You can find me on LinkedIn or Twitter.